We were looking at crazy clocks and checking out bars in section 2.4. Before we do that, there's a sign-up sheet here for a study group. Let's see if I can get that to show up on here. Well, that's going to take a minute to load. So do you have any homework questions? Yes.
Okay, so for the Mindscape 20.
Mindscape 20.
That's the only one I can get.
In 2.2?
2.4.
2.4?
Yeah.
So you're working ahead of us. So
You said we were going to go over that one today.
did I?
Yeah.
Okay.
So that's why I waited to ask you.
We maybe didn't get as far as I thought we would. Let's see. Yeah, I'd like to look at this one on Monday.
Okay.
So let's do that. I didn't make the assignment due until next week, right?
Yeah, you changed
Okay,
it.
that's good. And then did you have a question too?
Yeah, mine was the last question on this one.
So yours is in 2.4 also? Okay, let's go over those Monday and then maybe we'll get the questions answered right in class as we finish the lesson. Any other questions? Yes.
The last one, 2.3.
2.3?
I may have done it, but I wanted to understand why the answer
Sure.
is right.
Is it possible for an extremely large prime to be expressed as a large integer raised to a very large power? So the answer is no. Does anybody know why no? Here's what they're trying to say, okay? I'll put this on the document camera. Once I can find the cursor. At home I make my cursors gigantic black arrows because I can't find them otherwise. Here we go. Let's get the question on the screen at the same time if I can. I think I can just make this window big, right? Well, let me do that. I don't want to write on it. Okay, is it possible for an extremely large prime to be expressed as a large integer raised to a very large power? So a large integer, this isn't the largest, but let's just say this one, expressed to a very large power. So 999 to the 999, that's a very large power. What does that mean when you use an exponent? Who remembers what does an exponent mean?
You multiply that number by that amount of times.
That's right. You multiply that number by that amount of times. So if we had 2 cubed, that would mean 2 times 2 times 2. So 9, which is 8. 999 to the 999 is 999 times 999 times dot 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 times 999. 999 times. Is any number to an exponent prime? So here's some smaller numbers to exponents. Are any of those prime? A prime number can't be factored, right? The only way to write it as a product is a product of 1 times itself. So here this is 2 times 2 times 2 times 2, or 16. 3 times 3, or 9. 5 times 5, or 25. None of these numbers are prime because they're written as a product. And that's why the answer in the Mindscape is no. Because you can't write a number to an exponent other than 1 and have it be prime. Okay, so if you had said 5 to the 1, that is 5, so that's prime. But you notice that's not a very large exponent. Okay, and actually I didn't pick a very large number that was prime like the problem called for, but it doesn't matter. If you have an exponent that's not 1, you're writing a product, so it's not going to be a value of a prime number. Any other questions? Okay. This is a sign-up sheet for a study group. So our tutor for this class is named Jake. Jake took this class. He would like to help anybody who needs help. In the first class, someone signed up here with they put an X though instead of a tally mark. So if you're interested in a study group at all, put tally marks at the times when you're free to go to a study group, and then the time period that has the most tally marks will be time periods that Jake will offer a study group. He's unavailable here, that's why these are crossed out. But otherwise, he's willing to set up a study group. So what he does in a study group, or what he's done in the past, is he goes over the things that he expects you'll be quizzed on, and he has you do the problems that he expects you'll be quizzed on so that he can see and check your work individually and see how you're doing. Online students, if you're able to come to campus and go to a study group, email me what times and I'll put tally marks in there for you, okay? All right, so this is going to come around the classroom. Let's see, I'll go this way, and then around it. Okay. So let's do this half of the room, and then when it's done with this half of the room, it'll go in the back and come forward. So put a tick mark if you're interested in a study group at any times that you'd be willing to show up. Before we go on to 2.4, there was one other thing. So a couple of students emailed me questions about the directions for the drop boxes. So if you go to your Dropbox, you should be able to see the directions. Let me show you where. So I tell you in class too, but it should also say in the directions if for some reason you don't hear what I say. Is that as a student right now? Yeah, okay. So if you pick out a Dropbox, so say this one, it should say in the instructions, upload a picture of your work, the instructions, upload a picture of your work verifying the UPC on the box of tissue that we did in class. So we'll be doing that later today. Does anybody not show that? I'm not sure why people weren't able to find that. Do you have a question? Okay. Okay, let's go on to what we were working on then. We were working on crazy clocks, and that was actually a technique called modular arithmetic. So let's pick up there, looking at modular arithmetic. What we're doing in this section as a life lesson is to explore ideas systematically, investigate consequences, and formulate general principles. So we're going to explore this modular arithmetic and see what we can make with it. So for example, I had you take a regular old clock and see how much later it would be 38 hours later. What we were doing was arithmetic mod 12. So we were taking the 38 hours and writing what it was equivalent to mod 12. So this little symbol with the 3 bars is read equivalent to. And what we were doing with the 38 hours is we were taking out sets of 12, and that's why it says mod 12 here, because you're taking out modules of 12. So the 38 equals 12 plus 12 plus 12 plus 2. So the answer is that 38 is equivalent to 2 mod 12. So when you do modular arithmetic, you're actually looking at the remainders. If you took 38 divided by 12, you'd have 3 remainder 2. Okay, so you're actually looking at the remainders when you do modular arithmetic. Let's try another example. So we had a clock that had 7 hours on it, and I said, well, what time will it be in 211 hours? And what you're doing then is modular arithmetic mod 7. So we take out multiples of 7. Now that's a big number, so you would use your calculator. So you take 211 divided by 7 and you get 30.1423, and so that tells you that you can get out 30 multiples of 7. So 30 times 7 is 210. And when you subtract the 210 from the 211, you get 1, so the remainder is 1 here. So 211 is equivalent to 1 mod 7. So what we want to do now is spend some time making sure you feel pretty good about doing modular arithmetic. That is something I will ask you to do on the quiz, so let's take time to make sure you're pretty good at it. Let's do mod 5 because that's easier, since everybody pretty much knows their multiplication tables with 5s. Now, you don't have to have the underline. I'm just putting the underline there to show where you're going to fill in your answer. So we're thinking about 12. What is 12 mod 5? What is 12 equivalent to mod 5? So 12 is equivalent to 2 mod 5 because you have the multiples of 5 that come to 10. So you have 2 mod 5. Here, I'll write down a number. Well, how about 37? So mod 5 you can maybe even do in your head, right? Because you just think about how much more than a multiple of 5 it is. Can anybody do 37 mod 5 in their head? 2, yeah, right, 2, because it's 2 more than 35, isn't it? So if you divided 37 by 5, you'd get 7 remainder 2. So 2. So you're looking at the remainders when you do modular arithmetic. Here's one. What is 60 equivalent to mod 5? Yeah, 0. Because 60 divides evenly by 5. So when you go to take out the multiples of 5, there's no remainder. So when you do modular arithmetic, you get a smaller number here, and the number is always smaller than the number at the end that you're doing modular with. Like when we do mod 7, we get an answer between 0 and 6. When we do mod 5, we get an answer between 0 and 4. I'll write down several problems for you to try. And then I'll come around and see how you're doing. We'll work with mod 6. And we'll do one big one. So go ahead and simplify. 13 is equivalent to what mod 6? 21 is equivalent to what mod 6? 18 and 4, 17. What are those? All mod 6. If you think you have it, raise your hand, or if you're stuck, raise your hand. Especially if you're stuck, raise your hand, because I don't have time to check everybody's. In fact, I can't even see anybody's without some light on here. Wrong side. Try these lights. Okay.
You're catching on.
So 21. So that's a half of a one, it's not like that. So the three is what you're interested in at. So take 3 times 6. Subtract that. Why did you not know? Can you do that again? I think we did it. Oh, this one, okay. So, yeah, so 21. Yeah. Yeah. So you're looking for, take the whole number that you got in the calculator. Everybody stop. Okay, so I don't always have time to see everyone's, but I'd be happy if you would stop up after class to look at this. So in your calculator, you get 2 point something here. You're interested in the 2, because then you take the 2 times the 6 is 12, and that's what you're going to take away. That's what you're going to take away from the 13. So you want to take multiples of 6 away from these numbers. So you have to find how many multiples go in. And when you put the 21 divided by 6 in your calculator, you get 3.5. The 3 is what you're interested in, because then you say 3 times 6 is 18, and 21 minus 18 is 3. So that's how you take multiples of 6 away from the 21. You actually find out how many times the 6 goes into the 21, how many whole times, and subtract those away. So 6 times 3 is 18, so we're going to get 0 there. 417 is a big number. 417 divided by 6 is 69.5. So the 69 times 6 is how many multiples of 6 I can take away. 414, yeah. So 3 is the answer then. You get how many full multiples of 6 can you take away from your number? And then if you take the 69 times 6, that's 414 total, and that's how many multiples, that's how much you get when you take away 69 multiples of 6. Any questions on any of those? Doing modular arithmetic can help with doing some big multiplying. So computers can use modular arithmetic to make the work easier, and that's one reason they can multiply and add much more quickly than they can divide or subtract. So let's look at some bigger numbers here. So we have this big number, 200 times 3 plus 421 times 2, and we want to know what that is mod 5. So what we do is we look at these big numbers mod 5 off to the side. So if you take 200 mod 5 and you simplify it, you're going to take out multiples of 5. Well, that's 0, isn't it? Okay. Because 40 times 5 equals 200. So when you take away multiples of 5 from 200, you have nothing left. So this is the same as 0 times 3 right here, which is certainly easier to work with. And then we do the same thing with 421. So 421 is another big number in our work, so we can make it simpler. So you're looking at multiples of 5, and you can probably do that in your head, but in case you're more into using your calculator, 421 divided by 5 is 84.2. And the 84 is the part that tells us how many complete multiples of 5 you can take away. 5 times 84, that would be 420. So when you take the 420 away from the 421, there's 1. So we can change the big number, 421, to just be a 1, since we're working mod 5. Does anybody have any questions on switching out those big numbers? So you have the 0 times 3, which is 0, and the 1 times 2, which is 2. So we get 2 mod 5. So the answer is 2 mod 5. Yes?
I didn't catch with the 421 that way below divided by 5.
So
Multiplied by 5 and not the decimal.
So we're changing 421 to mod 5. And so when we divide out 5, then we get 84.2. We're interested in the 84 because that gives us complete quantities of 5 that you can remove. So you can remove 84 complete multiples of 5. So figure out what that is. 5 times 84 is 420. So 420 is what we are removing from the 421. Okay, yes?
I have a question so I understand. 2 mod 5, is that 2, like, if you look at D, like 417, that example, is that 2 like replacing what 3 is?
Yes.
Okay.
So I could have put an underscore there.
And then like what that's equal to is that equation that we started with? Like?
Yep, this whole thing would be like where the 417 was.
Okay, that makes sense.
Any other questions? The notation's kind of weird, isn't it? It's like trying to get used to that. Let's try another one. How about How about some exponents? Exponents are a really good place to do modular arithmetic. So we're going to simplify 2 to the 300th power mod 7. Now notice if you put 2 to the 300th power in your calculator, what a mess you get. We have 2.037 E90. What does that even mean? Does anyone know? What does the E90 mean? Anyone know what the E90 means there on the end of my calculator printout?
It's scientific notation.
It's scientific notation. It means times 10 to the 90th power. So it means you can move your decimal place 90 places to the right. So this is a really big number. It has 91 digits because you'd have 2 and then 90 more digits after it. We can find out what this is mod 7 without first finding what 2 to the 300 is if we first work on the 300 mod 7. So we're going to take out multiples of 7 from the 300. So when we divide the 300 by 7, we have 42.86. So 42 full multiples of 7 can be subtracted away from the 300. Let's see what that is. So 294 can be subtracted away from 300. Remember, this was just like if you were calculating in weeks, when we were calculating what day of the week a particular day of the year fell on, and we were just taking out multiples of 7 to take out weeks. Well, we're doing that the same thing with just multiples of 7 where they're not representing anything. So we take out 294, which is 42 multiples of 7, or 42 weeks, and that leaves 6. So 2 to the 300th mod 7 is equivalent to 2 to the 6th mod 7. And 2 to the 6th is much more manageable. That's 2 times 2 times 2 times 2 times 2, 6 times 64. When you're fully simplified, you should have a number smaller than 7. Okay, so we keep going here. We simplify 64 now. If you know your multiplication tables, this will help a lot. We have 64 divided by 7 is 9 point something, 9.14, because 9 times 7 is 63. So when we take out multiples of 7, we want to take out 63 units, and that leaves 1 left. So modular arithmetic can make these exponents smaller. Let's go ahead and try another problem. Do you have any questions at any of the steps on this one? So let's simplify 2 raised to the 281st power mod 7. So another big exponent that we can simplify. So let's find what 281 mod 7 is. So if you divide 281 by 7, you have 40 point something. because the 40 times 7 is 280. So when we're taking out multiples of 7, we take out 280 units altogether. So 2 to the 281 mod 7 is the same as 2 to the 1 mod 7. So that's just 2. That time we didn't have to simplify at the end. Anybody have any questions? Well, you should be having questions. You should be wondering, why am I learning this? What do you do with this? Well, besides just being fun, we use modular arithmetic in the real world quite a bit. From your textbook, we have written down modular arithmetic helps us find errors in grocery prices, our checking accounts, UPS package deliveries, airline tickets, and driver's license numbers. So to just look at an example of that, we'll look at universal barcodes. I brought some universal barcodes with me, but it would be more fun if somebody had a universal barcode that I didn't know. Does anybody, can you look through your belongings and see if there's anything with the 12-digit universal barcode?
I have a hand sanitizer.
Oh, good. Okay. Can you count and see, is there 12 digits on it, including the little ones? Sorry.
Yeah.
The little ones under here.
Yes.
Yeah.
Then I have one.
Okay. Oh, that's good. Okay, we'll try yours after. I'll do yours first, though, because you told me. So tell me 11. I'm going to tell you the last one, so don't tell me the last one.
Okay. So 6, 6, 7, 5, 4, 8, 3, 4, 9, 1, 7.
Okay, so that's 11, right?
Yep.
Okay, so there's one left, and I'll be able to tell you because the way the universal barcodes work use modular arithmetic. And the first 6 digits identify the company that makes it, the manufacturer, and the last 5 digits, the next 5 digits tell the product itself, and then there's 1 digit that's a check code. So this last digit that's a check code, I'll be able to tell you, because what we do is we have a little pattern here. We take each digit and multiply the first one times 3, the next one times 1, then by 3, then by 1. So it just goes times 3 times 1 times 3 times 1. So the check code gets multiplied by 1. So we take the universal barcode and we take alternating digits. Start with 3 times 3 times 1 times 3 times 1 times 3 times 1. See what we get. So we have 18, 6, 21, 5, 12, 8, 9, 4, 27, 1, 21. And then we add all these up. You get 132 and plus this question mark, but it needs to come out to be equivalent to 0 mod 10. Mod 10 is the easiest to work with, right? You can take out multiples of 10 most easily. So that means the check digit should be 8. Is the last digit 8? Oh, good. They don't all do it, so it's all good. Is it gonna work? Yeah, so the last digit is 8, that meant. Because then I'll get up to 140, which is equivalent to 0 mod 10. So mod 10 is the easiest, because if you're doing mod 10, it has to end in a 0. If you want to be equivalent to 0 mod 10. Okay, let's try another one. Do you want to tell us, was that you who had one?
Yeah.
Okay, you want to tell us the first 11 digits?
8, 9, 1, 3, 2, 5, 0, 0, 4, 0, 6.
Okay, so we have one that we're going to find. Okay, so this is again something I would ask you to do on a quiz, to take a universal barcode and find the missing check digit. So times 3, times 1, times 3, times 1, times 3, times 1. So on your 3x5 card, you'd maybe put an example or show yourself that it's the pattern times 3 times 1 times 3 times 1, starting with the 3, because that's not something that people usually know. So the last digit is 0? Yep, because this adds up to 80. So 80 is already equivalent to 0 mod 10, so we don't want to be adding any more digits in there. Okay, who else had one? I thought I saw another hand. Yes?
I have one.
Okay, and what is yours?
Hold on, I might not have one because I think there's a number missing.
Oh, okay. Yes, what is yours?
0, 2, 0, 2, 4, 2, 0, 0, 0, 0, 0.
Okay, and then there's one left.
Yeah.
Okay. All right, so this one, can you work this one at your desk and see what you get? Does anybody else have a product made by the Mountain Dew Company? It'd be fun to check the first 6 digits against the first 6 digits. Yes? Do yours start with these? The first 6 digits?
No.
Huh, weird. Okay. I'm not sure why that. Maybe they're made in different places because one's in a can and one's in a bottle. I don't know. Or maybe we'll find one that doesn't work. Because remember that this was a rule that most universal barcodes follow this, but there's some that don't. So let's see what we got here. Was that 2? No, not 2. Did everybody else get 18 then, that this adds up to 18? Okay, so maybe that's why your 2 Mountain Dew products don't work. Maybe Mountain Dew doesn't use the same universal barcode. Well, the one that, did you find out if yours Did you find out if yours
Yours is missing a number.
missing a number? Well, the one that you're supposed to upload in the Dropbox is the Kleenex. So let me show you the Kleenex one. Okay. So you can just work the whole thing out here, okay? So just write it out. You don't have to find the check digit. Just go ahead and work out the arithmetic and verify that it does indeed come out to be a value of 0 mod 10.
Is that 36,000?
Yes, it is. 036,000,214,000. So multiply times 3 times 1 times 3 times 1 and so on. And you should get a sum of those values to be 40. 40 is 0 mod 10. Anybody have any questions? Well, this universal barcode scheme will catch if one digit is wrong. So if you are writing down digits and you miss one, and then you handed the sheet to somebody who was giving you a rebate or something, they know that you were off by one. I imagine they probably just watch what you say and look at compared to what they have. But if they don't have something to check against, then they can tell that you're off a digit. Okay. Let's go ahead and look at what you would check on a bank. So if I have this rebate check, the checking scheme for a routing number is more involved. So I got a rebate in the mail, which I already deposited electronically. But the routing number on your accounts, on your checks, is the number between these two little vertical dots with the vertical line next to them. So the routing number here is 091981811. 091981811. So that's the routing number. You know, when you go ahead and submit your income tax and you want to make sure you put the correct routing number on, and your bank account too, so that it gets into your bank and your bank account. This is checked using mod 10 arithmetic as well, but it's a little trickier scheme because it will catch like 2 errors instead of just 1 error. So the way this works is you multiply times 7 times 3 times 9 times 7 times 3 times 9 times 7 times 3 times 9. So a little more tricky, right? You're multiplying by 3 different numbers, 739, 739, 739. And this should come out to 0 mod 10. as well. So we get 0, 27, 9, 63, 24, 9, 56, 3, 9. What does that add to? $200. So 200 is 0 mod 10. So a little more complicated scheme for routing numbers because those need to be more secure. If you're interested in this type of work, you can see it used in encryption if you look in section 2.5. So section 2.5 talks about how this modular arithmetic, along with the prime numbers, remember we talked about big prime numbers, how important they are? Well, we see the modular arithmetic along with the prime numbers working together, and your author works through an example if you're interested in that. We're going to go on to section 2.6. And section 2.6 is going to need a little bit of algebra review. So we're just going to do a few minutes of algebra review today. Do you have any questions before we go to 2.6? So first we're going to remember how to solve equations. Remember, when you have an equation, you have that equal sign that makes an equation. It means the two sides are equivalent. In fact, the two sides are like a balanced scale. So the right side says 5, and that means the left side is 5 as well, even though it's written as 2x plus 3. So when you work with an equation, you have to remember, whatever you do to one side, do to the other. And just like with a scale, that will keep the two sides equivalent. Like on a scale, if you take off a pound, you got to take the pound off of both sides for the scale to stay balanced. So what's the first thing we do here to solve for the x? Good, subtract 3, and you do that from both sides. So that's like making your balance scale now have 2 pounds on both sides instead of 5. So again, they're still equal though. And now, of course, you would divide both sides by 2, and x is 1. So I just wanted to remind you, when you have equivalent values, the equation stays true as long as you do the same thing to both sides of the equation. I also wanted to remind you what square roots are. So when we use the square root symbol and say the square root of 4 is 2, we mean the square root of 4 is 2 because 2 times 2 is 4. Or if I say the square root of 25 is 5, that's because 5 times 5 is 25. Now when we have something that's not a perfect square, like the square root of 7, that would be the exact value. You can put the square root of 7 in your calculator and get an approximate value. The mathematicians don't like approximate values. They want exact values. That's because if you take this approximate value and multiply the 2.64 times 2.64, you get 2.64 times 2.64 is 6.9696. Whereas if you take the square root of 7 times the square root of 7, you get exactly 7. So mathematicians want exact values, and so we use the square root of 7 and don't write down the 2.64. I can show you what happens when you start rounding off. You can get chaos. There's a section of your book 7.6 called Predetermined Chaos. And in that section, we have some arithmetic going on. You see the two sides of this table are the same. Same. And in both columns, they're doing the same step. They're multiplying by 180, and then they're taking the sign of the value, which you could do if you want to. But notice right here they round off. So they just round off to the 10 millionths place, and then they keep going. So this one step, number 5, they round off to the 10 millionth place, and they keep going. And look how different it is at the end. 3/10 different when they only rounded off 10 millionths. So we don't want to round off. We want exact values, and this is a good example why. We'll look at some more algebra review and the rest of 2.6 Monday. You have a good weekend.